Today we are going to start Chapter 19. Chapter 19 is thermodynamics. So we are going to be talking about entropy in today's video, which hopefully you'll remember from Regents Chem. We will do a lot of Chapter 19 now, and we will finish up a few subsections of Chapter 19 in the spring. In addition to entropy, the other big thing that we are going to take a look at in this chapter is if a reaction is thermodynamically favorable, or in other words, is spontaneous. So therefore, it can proceed without outside intervention. All reactions should be spontaneous in one direction or the other. We have a lot of examples of things that are spontaneous at one temperature and non-spontaneous at another. A nice easy one to visualize would be ice melting and or freezing. So if we are above 0 degrees Celsius, above 32 degrees Fahrenheit, then ice would spontaneously melt. If we are below 0 degrees Celsius, then water would freeze spontaneously. So we will learn how these systems are dependent upon temperature, and we even have an equation so that we can calculate the temperature where they switch from thermodynamically favorable to not thermodynamically favorable. I do want to take a moment to point out something that is sometimes a misconception. So just because a reaction is thermodynamically favorable or spontaneous does not mean that it occurs at a fast rate. So the speed of the reaction, that has to do with the kinetics of the reaction, and that is dependent upon the activation energy. So we have some spontaneous reactions that occur very quickly. We also have some that occur very slowly, such as rusting. So please keep in mind that the speed of the reaction is a completely different thing than whether or not it is spontaneous. All right, so our main topic for today is entropy, which is abbreviated with capital S. So delta S would be the change in entropy, and that measures the randomness of the system. It is related to the motion of the molecules, and it is largely determined by what physical state the substances are in. So when we have things that are existing in the solid state, that is a lower entropy because particles in the solid phase are lined up neat, orderly. They are not very chaotic. They are not very random. So they have a lower entropy. When we have things that are in the gas phase, that will correlate to a much higher entropy because the gas molecules are moving all over the place. So we have a lot more motion. So most of the time, we can take a look at a reaction, and just based upon the phases, we can determine whether or not entropy would be increasing or decreasing. So as we said on the previous slide, entropy when you have something in the gas phase is going to be higher than that of the liquid phase, which would be higher than that of the solid phase. So things in the solid phase are going to have the lowest entropy. And that's because entropy is related to the motion of the molecules. And as the molecules are more free to move, their entropy increases. So that obviously happens in the gas phase. In the solid phase, they are only vibrating. They're not moving all over, so they are going to have less entropy. So as we have already said a couple of times, we will have a higher entropy when we are in the gas phase and a lower entropy in the solid phase. So first thing you want to do when you're asked about the change in entropy is to take a look at the phases that are present. Now, when we have an aqueous solution, generally speaking, as our solute dissolves in the solution, the entropy would be increasing because the arrangement of particles is less organized. Also, there is more movement of those ions. We've already said that if we're trying to predict what will happen to the entropy, you should look at the phases. But sometimes the phases remain the same throughout the course of the reaction. So in this example here, our reactants are gases, and so is the product. Therefore, your tiebreaker will be the moles or the coefficients. So in this particular example, we would have 3 moles of reactants going to 2 moles of reactants. Therefore, the entropy would be decreasing because we have same phase but less moles. So there would be less molecules in there, so it would be less chaotic. And there's also less motion because there's less molecules in there. There would be less moles in there. Now, the more advanced way to take a look at entropy is dependent upon microstates. Microstates are basically like a snapshot of the molecules at every millisecond. So if you had something in the gas phase and you would take a bunch of snapshots, the molecules would be different in those. So they have more possible arrangements. When you have more possible arrangements, more microstates, that will increase the entropy. When you have a solid, if you took a snapshot every millisecond, there would not be as much variation from snapshot to snapshot, so there's not as many microstates, so it has a lower entropy. Now we've talked about more motion with our molecules equals a higher entropy. We should talk about there's different types of motion. So translation is where the entire molecule moves. In translation, you would start with your molecule in one position and then it would switch to a new position. In vibrational movement, the atoms in the molecules move away and towards each other. So essentially, the bonds are flexing, they're lengthening and shortening. So this is only going to happen when we have bonds present. So if you have a monatomic atom, there will not be vibrational movement. Rotational movement is the molecule is spinning on its axis. So what could a single atom do? So a single atom could rotate, and a single atom could move from one location to the other if it was not in the solid phase. So rotational and translational is what a single monatomic atom could do. A solid can do rotational and the solid can do vibrational if it is not a single monatomic atom, if it has the bonds there. So it may or may not be able to do vibrational depending upon what it is. Okay, so we have some quick region style. Is entropy increasing or decreasing in each one of these examples? So in our first example, H2O liquid to H2O gas, you're going from a liquid to a gas, therefore the entropy would be increasing. In number 2, we're starting with an aqueous solution and going to a solid. So it would be an aqueous solution where the water is getting evaporated. So that would be decreasing because you're forming a solid, so the entropy would be decreasing. And then in our final one, We have a solid and a gas going to a solid. So therefore, the entropy would be decreasing because we were part solid, part gas, so part low entropy, part high entropy to a solid. So that would be lower entropy, so we would be decreasing. All right, the second law of thermodynamics states that the entropy of the universe, so the whole entire system, is increasing when we have a spontaneous process. And the entropy of the universe overall is not changing when you have a reversible process that's able to proceed in both directions. All right, just like energy and enthalpy, entropy is a state function, meaning that we can only measure the change. So it's going to be dependent upon the final and the initial. So we are really going to be talking about the change in entropy. We are going to use Appendix C again in the back of your book on page 1059. We used these with our delta H calculations. We are going to do the exact same calculation except for entropy. So it would be the change in entropy is equal to the sum of the products minus the sum of the reactants. So it's going to be essentially the same formula that we use to calculate the heat of the reaction using Appendix C. Now, these are some entropy values. And if you take a look at this chart, we can see that these numbers support things that we would have already known. So, for example, things that are existing in the gas phase have higher entropies than those in the liquid or solid phase. So we already knew that, and this just confirms that. Also, within the same phase, so if we take a look at our gases, as the molecules get larger, they contain more atoms and more bonds. You can see that the entropies are increasing as we move down. Now that is because as there's more bonds, there's going to be more vibrational movement. To answer the questions on this page, we want to have our books out and we want to be looking at Appendix C on page 1059. Now for number 1, we probably do not need the textbook. We know that CO2 gas would have a higher entropy. Same thing with argon. We know that argon gas would have a higher entropy because they're gases. But for number 2, we do want to take a look at these hydrocarbons. So we have methane, ethane, propane, and butane. If we look, methane has an entropy of 186.3, and that would be joules per mole Kelvin. Then we have C2H6, that's ethane. The value is 229.5 joules per mole Kelvin. So that's what we would expect to see. The entropy is increasing because the molecule is getting larger. There would be more bonds, so the vibrational movement would be greater. Then we have C3H8. That is 269.9 joules per mole Kelvin. So again, increasing as the molecule increases. Then we have butane, which is 310. So that is also increasing. So as the number of carbon atoms increases, the entropy increases because there is more rotational movement. However, if we look a little bit closer at Appendix C, then C4H10 could also be 231.0 joules per mole Kelvin. So this is the value that butane has when it's a liquid. So once you switch from gas, which the other hydrocarbons are gases, to a liquid, then you start to see the entropy decreasing. So to answer our question for B, as the carbon atoms increase, the entropy increases if we are maintaining the phase. However, if we change phase, then the entropy would decrease. And by change phase, I should have said, as we go from a gas to a liquid, even though they're getting bigger, the entropy would decrease. All right, last thing that we are going to talk about in this video is our change in entropy calculation. So just like we did the change in enthalpy, where we did the sum of the products minus the reactants, we will do the same thing and also use Appendix C to calculate the change in entropy of a reaction. Now we already should know if our value is going to be positive or negative, just looking at the equation and predicting whether or not entropy would be increasing or decreasing. But this then would give us a numerical value for it. All right, so now we're just going to do a quick example using change in entropy is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. So first thing we want to do is to just start plugging into that equation. Now we do have to take moles into account. So we would do 2 times the entropy for NO2 minus 1, because we only have 1 mole of the N2O4 minus the entropy of N2O4. Now we will look those values up on Appendix C. All right, so NO2 has a value of 240.45 joules per mole Kelvin, and N2O4 has a value of 304.3, which makes sense because that has more bonds in it. So it would have a greater vibrational movement. Once we do our math, we get positive 176.6 joules per mole Kelvin. And that does make sense. Entropy is positive, and we should have already predicted that the entropy would be increasing because we are maintaining the gas phase, but we are producing more moles of our product, so therefore there's more molecules, there would be more movement.